All right. Well, we're getting started. So welcome everybody to another session or another program, another episode of the Zoom Rock Room. As always, we have something awesome planned for this evening. Hopefully something that you gain, that you learn something new this evening. But of course, we got to start our night out with a couple of jokes to get us in the mood, to get us in the theme of what we're going to be talking about this evening. So Jerry, what is a dinosaur's least favorite reindeer?
Oh, least favorite reindeer. I don't know that one.
Comet.
Oh my gosh. You're exactly right.
That's so appropriate for tonight.
Thank you. I tried.
We worked on hard on this all week. Difference is a difference in between a hamburger and a shooting star. While one is meaty, the other is a little meatier.
Why did the asteroid quit his job and move to LA?
I don't have that one either.
He wanted to be a stand-up comic.
I got one more for you then.
Okay.
New article about an asteroid colliding with the Earth in the near future. I couldn't read it. It hits too close to home. All right. We'll get into our introduction, and I personally welcome you all on board again. Or if you're new ones, oh, Jerry, you didn't do that right. I gotta share first. I get all ferhoodled with the after the jokes. There we go.
All right, Zoom Rock Room with that brand new logo.
That's beautiful. Thanks, Andrew. We like your work, Andrew.
You're welcome. Thank you.
As always, Zoom Rock Room is sponsored by Lair Architecture out in Arizona in Lake Havasu City. Designed for the future is their little motto there in quotes. Feel free to shoot them an email, say hi. Or if you have any questions for them, need any advice, they would be more than happy to help with any of those questions. The Dirtman Report, as always, I assume we're going to see one tonight. We normally see one every Zoom Rock Room. So hopefully we're going to see one tonight before he uploads it and publishes it on Facebook, as Andrew always does. Always funny, always educational. He's super expressive, so he's really easy to follow along with on his videos and understand what he's talking about. Always entertaining, always educational. So like I said, hopefully I think we're gonna see one tonight, and if we do, I guarantee it'll be fabulous as always.
Yeah, I don't think we'll see a video tonight, but Andrew, I want you to announce what you did this past week. That will be shown next week.
Okay. So you want me to announce?
Okay. Oh, should I do it? Okay.
Yep, you do it, Andrew. Sorry.
Are you talking about the podcast?
Yes. Yep.
Okay. All right. So yeah, I was just talking about Susquehanna Riverkeeper.com. It's Susquehanna Riverkeeper.com. But John Zaktansky contacted me to do a podcast with him. He's done a podcast with professors and all kinds of different things on the river. And he contacted me to talk about the history of the geologic history. So we did about 20-minute podcast, and that'll be coming out this week. I got a lot of tips from Jerry. So some interesting facts will be in there provided by Jerry. But other than that, it was a great podcast. And yeah, I'm not sure when he'll finish it. It should be in the next couple of days. And it'll be up on Middle Susquehanna Riverkeeper.com.
Okay, we'll keep you advised of that. Thank you, Andrew, for doing that history there.
Not a problem.
The Institute Waynesboro, we have the red box around the two geology programs we're doing actually in May. May 4th is the indoor program at the Church of the Apostles in Waynesboro. That is actually going to be called On the Other Side of the Mountain, which is mostly the geology of York County, because 2 days later, May 6th, you can take a bus tour from Waynesboro into York County and see about 10 different sites of different geology of York County. It's going to be a 8:30 to 6 o'clock day on the bus ride. So we'll keep you hopping for 10 hours plus a nice lunch at Sam Lewis Park. So you can check out their website at info@natureandcultureinstitute.org for the prices for non-members and for members. It's always a fun day. It's a fun evening Thursday night to see all the people that do come out to the Church of the Apostles. Crystal Grove Collective, another sponsor of ours, with Michael and Krista at the Lower Island Shopping Center in Camp Hill, Pennsylvania. They have a huge store there, plus workshop rooms, a conference room, and they are going to be starting up some programs during the year. They're also at the Morning Sun Market in York. Actually, it's in Thomasville, near the York Airport. If you are in the York area, they are open there Saturdays and Sundays. Big flea market sort of atmosphere. Franklin County Rock and Mineral Club is this coming weekend in Chambersburg at the Eugene Clark Community Center in Chambersburg. It's a brand new location for the Franklin County Rock and Mineral Club show. So again, if you're going to be in the Chambersburg area, stop by and see Tom Smith and all the members of the Franklin County Club. It's always a good show, and lots of dealers to take your money or credit cards along to buy some of your favorite gems, minerals, fossils, rocks. Youth Archaeology Week is coming up in June 19th to the 23rd at Cador State Park. Ages 9 through 12-year-olds, and we're doing rather nicely on registrations. We're limiting it to 24 students, and we're about 2/3, 3/4 of the way filled at this point. So it's going to be a good week of archaeology. We're digging in the area of the Mary Ann Furnace, the oldest furnace on this side of the Susquehanna River. So it's a very important site, and we're going to try to learn more about Mary Ann Furnace than what we learned in 2010 and 2011 when we were last there. Melanie.
Sure thing. So our Zoom Rock Room schedule for the next couple sessions, next couple weeks. Jot these down if you haven't already. Put them in your calendar. Take a picture with your phone. April 4th is our next one. And we'll be talking about that Mary Ann Furnace in Hanover, PA, like Jerry had just mentioned for Archaeology Week. We're going to go into depth on that. On April 18th, Rock County 101 with Jerry and myself. On May 2nd, mine, Montgomery County and PA with Ron. That also should be extremely interesting. May 16th, after that, I can't believe we're already talking about, mid-May, end of May. We're going to be hearing from Paul. He's going to be talking about the history of the search for the ideal stone. Sounds obviously very interesting, just as the rest. And June 6th. It's going to be a mystery to us all what June 6th holds for us.
It could be, yeah. All right. And that's the end of our introduction there. The title, by the way, the Potomac Marble in Search of the Rock is actually the name of his book that Paul Krengold has written from Maryland. So you may be interested in purchasing that before or after his talk. I've not personally met him. I saw him on the internet. In fact, I think one of our Zoom Rock Room members sent me his information. Said this might be a good speaker. So I contacted him, and he was very happy to come on board. So other announcements, I I did send out the flyer for this Saturday's geology walk at the Susquehanna River Hills State Park in York County, Saturday at 1 o'clock. As you know, the weather is sounding pretty bad for Friday and Saturday. So we're kind of on standby if that's going to be held that on Saturday or not. You can email me if you want to go and you're not sure if we're going to have it or not. Come Friday or Saturday. I did text the park naturalist to see what their policy is. I know it gets pretty muddy back in those hills when it rains, so we'll see what's going to happen with that. So, you have anything else you want to say at this point in time there, Miss Mill?
I don't believe so. I'm interested to hear from our guest speaker this evening.
Okay, I am too, because we got to thank our room member Joseph for getting Dr. Greg Herman into the room, and we've been looking forward to his program since he got scheduled. So I'll tell you a little bit about Dr. Gregory Herman. He earned his bachelor's in geology from the Ohio University in 1982, and after receiving a master's in structural geology from the University of Connecticut in 1984, he joined the New Jersey Department of Environmental Protection and began regulating industrial facilities that were discharging hazardous waste to groundwater. He transferred to the New Jersey Geologic Survey in 1985 to map bedrock geology in northern New Jersey and co-authored a revised state geological map in 1996. That's really cool. I like that. Afterwards, he managed his their GIS computer lab, and developed the program's first internet pages while earning a PhD in geology from Rutgers University in 1997. In 2001, he became the survey's first research scientist and obtained grants to study and characterize the physical properties of fractured bedrock aquifers using borehole televiewers and heat pulse flow meters to identify and catalog subsurface water-bearing features. Having retired from the New Jersey Department of Environmental Protection in 2019, after 33 years, Greg now teaches earth science at local colleges and works for Trap Rock Industries. And he recently has authored 2 books on impact tectonics and other natural phenomena, and provides earth science themes and online geotools for public use through impacttectonics.org. So obviously he's going to be talking about impact tectonics tonight, which is why we were talking about comets and asteroids and meteors tonight. So like my privilege to introduce to you Dr. Gregory Herman.
Well, thank you. That I probably should have abstracted the introduction, but I really appreciate the opportunity to come and share with you some of the research that I've been conducting over the past 20 years, really. And something that you probably don't hear of on a regular basis, if not ever, because I have, after 40 years of studying geology and doing a lot of different things, as the introduction indicated, I have come to the conclusion that our plate tectonic theory is extremely anemic with respect to the causative agents for mountain building and basin formations on Earth. And this couldn't have been possible without a background that integrated the geophysics, the geology, and the geographic information systems. And what I'm going to show you tonight is what I think are far-reaching strains on Earth and on Mars that I've looked at pretty closely, and can account for sudden upheavals in mountain building that doesn't take eons, but can form instantaneously as a result of large hypervelocity asteroid and cometary impacts. So let me share my screen. And let me know if you see it. And I will go into presentation mode once when it appears. Is that good?
You are good. Yep.
Okay, so if all of this information can be accessed through my website at impacttectonics.org. The title of this book is Punctuated Tectonic Equilibrium. And as drawn from evolutionary paleontology, I'm also proposing that it's as suitable as the guiding principle for terrestrial tectonics, as opposed to the gradualism and uniformitarianistic viewpoints that we currently hold. So very large hypervelocity, that is greater than 10 kilometers per second, comet and asteroid impacts, collectively known as bolides going forward. When they hit Earth and Mars, they impart far-reaching impact tectonic strain fields and spur geodynamic changes that are unaccounted for in current plate tectonic theory. I came to this realization after integrating geographic information systems data, including plate drift in red, vectors of horizontal plate drift gained from ground fixed global positioning systems around the continents. And when I plotted them up, you can see that the entire North American continent, north part of South America, rotate in concert around the point of the impact on the Yucatan Peninsula, which is the Chicxulub impact, at 66 million years, which wiped out the dinosaurs and other fauna, one of the great extinction events on Earth history. In our own backyard here, this is where the Chesapeake impact hit at the mouth of Chesapeake Bay. And I spent my entire career mapping up in the foreland between the Adirondacks and Chesapeake Bay, looking at the structural features, the geophysics, and it came to realize that much of what we were ascribing to Alleghenian Paleozoic mountain building episodes was caused by this hypervelocity impact that scalloped out Chesapeake Bay 35 million years ago. So we have two big events that help form the current tectonics, will stage the current tectonic events and help form aspects of our continent that are catastrophic in nature and not uniformitarian. Now, punctuated equilibrium pertains to biological evolution on Earth because Harvard paleontologist and the Cambridge paleontologist Golden Eldridge in the 70s, after studying the taxonomic evolution of Earth's creatures through time, realized that instead of a phyletic gradualism, what they saw was extreme extinction events followed by events of radiative adaptation that they termed punctuated equilibrium. And here on this chart, a lot of these large extinction events that you see plotted as the histogram here with extinction occurrences and percentage versus time, current time on the right, going back to the time on the left. Each one of these era boundaries, sometimes period boundaries, are formed at the same time or are actually caused by these large impact events that like the one that hit 66 million years ago right here in Chicxulub. At the same time, we had large igneous provinces developed. And when you plot these things together, you see we have these periodic punches that occur, known impacts in purple, suspected impacts in blue that I'll be talking about briefly here and that are featured as part of this book. And some of the bigger ones, like the Siberian traps, corresponding to the end Paleozoic extinction event, the Congo Basin suspected event with the Central Atlantic magmatic province occurring here. A lot of these things, I think, are incited as a result of these large hypervelocity impact events. So not only is there pronounced biological extinction followed by radiative stages of adaptive evolution, but we also see these periods of rapid plate adjustment occurring after these large impact events. With respect to a Wikipedia definition of phyletic gradualism versus punctuated equilibrium, you see here with phyletic gradualism, you have these dendritic patterns in the progression of life's complexity through time, occurring at at serendipitous phases, whereas in punctuated equilibrium, we have catastrophic events followed by radiative adaptation by a number of different species at the same time. So plate tectonics on Earth results from both short catastrophic periods of planetary bombardment and accretion, followed by prolonged periods of stasis involving ordinary plate drift and reorganization. To draw again the parallel between tectonics and biological evolution on Earth. Biological revolutions can result from catastrophic disruptions, as we've seen with Chicxulub and the dinosaurs, caused by large bolide impacts that also spur the development of large igneous provinces and tectonic revolutions. These catastrophic agents that reset the clock through time. Some of the best visual evidence that you'll see for these types of processes stems from Mars, because Mars doesn't have active surface tectonics. Basically, what has happened there as a result of bombardment and accretion is preserved in the satellite remote sensing imagery. For instance, the largest volcano in the solar system, Olympus Mons, sits right here, right behind Tharsis Montes, 3 other volcanic constructs of large igneous provinces on Mars. This is what I suspect to be a large impact strewn field with the wrinkle ridges and mountains raised up over 3,000 kilometers away from where the impact strewn field is. And guess what? When you have these hypervelocity oblique impacts coming in at 45-degree angles, statistically, they don't come in normal to the planetary surface. Statistically, they come in at an oblique angle. And when you get these oblique impacts, you get stretching uprange, where you have decompression melting and igneous complexes forming in the wake of these things. And you can see it here on Mars very clearly. Some of the best well-known features like Valley Marineris being part of this impact complex. We'll go into this in a little bit more, but I did a statistical analysis of the structures associated with this from remote sensing mapping. Astrobleams, which I use to define these star wounds, these large scale scars on the planetary surfaces, were first defined in 1961 by Robert Dietz in a Scientific American article, and he called them star wounds. Root structures of ancient meteorites are exposed by uplift and erosion over time. So here we have the patriarch of plate tectonic science, Robert Dietz, including astrobleams on the basis of the Vredefort crater in South Africa, where you can clearly see blemishes associated with this impact preserved over 2 billion years ago. This event happened. Here are rings at 660 kilometers, 1,600 kilometers, and 2,900 kilometers that I drew around this thing in order to emphasize the radial nature of the strain fields associated with these events. Now, if we bring in the magnetics, you can see the magnetic disruption of the aeromagnetic expression of the global magnetic potential field. As a result of this, probably came in from the right and downrange to the left. Very, very old continental structure. So astrobleams, as defined by Dietz, stem from impact tectogenesis. When very large bolide impacts bruise, welt, and structurally disrupt a planet's crust and upper mantle during episodes of projectile bombardment and mass accretion. Our planet, the moon, all of our planets were formed by bombardment and accretion. And those processes, ladies and gentlemen, are ignored in our current plate tectonic theory. So astrobleams include the array of far-reaching secondary geologic structures like faults, folds that become radially distributed around a crater upon impact. Dietz recognized those around the Vredefort. So many ancient large craters are buried now on Earth beneath deep sedimentary basins. The Chicxulub and Chesapeake, the 2 on the North American plate that I've already pointed out to you, were found by remote sensing and well drilling. They weren't recognized scars on the Earth's surface. They were only found by subsurface exploration. So many of these things on Earth are masked because of active sedimentary processes, and we have yet to find many of them. And the moon, which does not have active tectonics, serves as a good reminder of just how common bombardment is, especially in the southern hemisphere, as you will come to see during this talk. Here is a photographic detail from the Clementine Joint Mission in 1994, showing the south pole of the moon and its nature of it being peppered. The same thing happens on Earth. I had done a lot of modeling, trying to understand the way that the energy gets absorbed and dispersed in the planet in order to understand why it forms these rings at specific radii around these astrobleams. And what I'm showing you here basically is the profile of Earth with the solid inner core, the liquid outer core, the lower mantle, and the upper mantle. The crust is just basically as thick as that line right there. So basically, we're looking at the lithosphere and asthenosphere here. The base of the asthenosphere being about 660 kilometer depth, and that's the basis of the 660 kilometer ring, because I think you have primary refractions, and reflections off of these different phase boundaries, where you return energy back up to the surface of the Earth and create small welts and fracture systems that end up focusing where mountains grow. Here are some of the models showing these strain shells of these astrobleam fractured astrobleams around the impact point. Some of the data that really started me down this path had to do with the GPS data. And when I plotted up all of the GPS motions again for the different plates that we had readings for, again, it shows this concert of movement around the Chicxulub crater, as if now 66 million years ago after this event, we're still trying to dispel the energy flux that took place there. And if you don't think that just the horizontal movements around the crater is enough to convince you that these things have geodynamic consequences, look what happens if you plot the velocity of the movements of the plate from the point of impact all the way out to the 29 to 3,800 kilometer distance through North America. What you see is a gradual increase in plate drift until you come to 2,900 kilometers and all hell breaks loose. 2,900 kilometers, ladies and gentlemen, is the distance to the liquid outer core, a major phase boundary on the interior of the Earth. And when you look at the structural disruption that has taken place around the Chicxulub impact, you see it's basically probably responsible for a major phase of excavation of the Gulf of Mexico, uplift of the Llano Plateau, uplift of the Laramide, one phase of the Laramide orogeny, and in its wake, plate fragmentation and large igneous provinces. So here's the way it looks in Google Earth with the strain field, the foreland downrange strain field associated with Chicxulub. By the way, Chicxulub was not just a solitary impact. The main impact was about a 20-kilometer asteroid, but there were 5 or 6 other small asteroids, fragments that occurred at the same time. And this was a very energetic event based on the fact that it wiped out pretty much all of the fauna, reptile fauna in North America. But here, scaled down, is the disruption associated with the Chesapeake, which is an order of magnitude smaller. So if this was a 15, 20-kilometer asteroid that caused Chicxulub, this was a 3 to 5 kilometer asteroid. Something about the size of Manhattan coming in, slamming into the Earth, and both coming from the south to the north. Again, a model, not of Google Earth this time. This is a SketchUp Pro model, a CAD model of the Earth, modeling the different refractions and reflections that take place off of these phase boundaries as a result of the absorption of ground energy associated with these hyperkinetic events. So we refer to rheological layering as the different phases of layering into the Earth, including the solid core, the liquid outer core, the plastic mantle. And I think what we're also seeing are effects 5,000 kilometers away from where these things hit. And I'll show you good evidence of that towards the end of the talk. And some of you by now are probably saying, well, what about the energy associated with this? Do we really have enough energy to ripple the Earth's surface and cause these mountains to grow instantaneously as opposed to over time? Well, here's the way that people determine that, okay? The absorbed ground energy from a hyperkinetic, hypervelocity strike is equal to some fraction of the total kinetic energy of the bolide flight. So you have the velocity of flight, which can reach up to 30 kilometers per second. Excuse me. You have the mass of the object, you have the density, etc. And ordinarily, planetary geologists think in terms of how much energy from the original kinetic flight of that screaming piece of rock when it hits one of these terrestrial surfaces, how much gets imparted into the ground. Well, they use estimates on their online calculators to the tune of 0.0001%, 1 to the 10 to the minus 4, 1 times 10 to the minus 4 energy gets into the ground from these hyperkinetic, hypervelocity impacts. And even the early proponents of impact theory and cratering have said that with the bigger objects and in the higher velocity realm, you can see increases up to 10% of the energy from the kinetic energy of flight being partitioned as absorbed ground energy. And intuitively, I would think it would be 10% or higher. But they say that a lot of the energies expended in comminution, that is the destruction of the asteroid, a lot of it is spent in energy and heat losses and things like that. But a reasonable estimate is 10% of the energy getting into the ground from one of these things. So when these things hit at any of speeds of 10 to 30 to 60 kilometers per second, depends on the flight of the planet and the flight of the asteroid, whether they're opposed or whether they're coming in at right angles. There are a lot of disruptions that occur that exceed the velocity with which ground seismic waves can be transmitted. And a lot of these plastic disruptions that occur in the lithosphere and in the asthenosphere, in order to release these melts, they penetrate down to 600 to 1300 kilometers depth before they get returned back up to the surface. So you have hypervelocity speeds of 11 to 70 kilometers hitting these plastic bodies in space, rocky bodies and plastic bodies. And these large deep fault systems propagate outward and follow these primary P and S wave refraction paths, but P and S waves can only be transmitted 4 to 9 kilometers per second. These things are coming in an order of magnitude higher. So there's a whole catalog of secondary structures that planetary geologists aren't accounting for when they're only talking about the dispersal of seismic energy. Again, the same refraction. Here's a 90-degree span of our planetary surface coming out at a refraction, mid-mantle discontinuity of 1300 kilometers depth. And if you've done geophysics before, you know that refractions reach the surface faster than reflections. So I anticipate that these refractions are bringing a lot of energy with them. If you take a look at the actual energy using one of these calculators that you can find online right now, with an impact velocity of 30 kilometers per second and an asteroid 12-kilometer diameter, you're talking about 10 to the 23 joules of energy being partitioned into the Earth suddenly as a result of one of these impacts. Chesapeake size, you got 10 to the 21 joules of energy being absorbed by the ground. The annual energy needed to move tectonic plates on Earth is on the order of 10 to the 19 joules. So instantaneously, when we have one of these large events, we're exceeding the annual output of work done in plate tectonics, introducing it suddenly into the equation. When you look at it per second, that's 10 to the 12 joules of work per second that Earth expends in moving its plates around through gradual processes. By comparison, the ground energy absorbed by the Chicxulub or Chesapeake size impacts are order of 9 million or about 1 million times larger than what our ordinary tectonics are when you consider the energy associated with that. Conversely, Dave Elliott, a brilliant structural geology, estimated the amount of energy required to move the largest thrust sheet in the Canadian Rockies into place. His estimate was 10 to the 19 joules. So you see the amount of energy we have coming in from these hypervelocity bolide impacts can raise mountains suddenly, not just gradually. If you do the modeling, you realize that these refracted energy paths and associated pseudotachyte faults, whatever fracture arrays. You're talking about welts on the surface of the earth that have about 4 to 8 kilometer amplitudes. And we're talking about the size of Mount Everest here, right? So you're just talking about minuscule deflections on the earth's surface that are responsible for raising whole mountain chains. When we look in our backyard, and again, I've done most of my work up in this area of the Pennsylvania salient. I did my master's work at the University of Connecticut, trying to understand the nature of this curve in the Susquehanna. Why is the Pennsylvania salient bent like this, the mountains there, whereas they're really not bent like this anywhere else along the entire length of the Appalachians? And I walked away from that master's thesis at the University of Connecticut confused, because every time I tried to restore the folds and faults across this Juniata combination, they all came back to the head of Chesapeake Bay. And we didn't know about the Chesapeake impact at the time I was doing that work. Years later, a colleague of mine plopped a book down on my desk about the Chesapeake impact, and it was like a light bulb went off in my head. Oh my God, that's what I'm seeing up there. So here plotted on this map are calcite bulk shortening directions caused by penetrative strains from what have been previously ascribed to Alleghenian mountain building episodes. But guess what, ladies and gentlemen? Those same strains occur in the Mesozoic rocks too, not just the Paleozoic rocks. So this entire region has been shortened 5 to 7%, compounded, packed as a result of this impact in the Chesapeake Bay, pushing everything to the north suddenly during the Tertiary period. We have a Westchester arch anticline where the gravels of lower Tertiary age are warped out in front of it. And we have these yellow spots, which are rhenium osmium isotope dates on faults that come up with Chesapeake ages from the mineralization. There's my thesis work with the retrodeformation of the Pennsylvania Valley and Ridge Province back to the head of Chesapeake Bay, and me walking away from this in 1984 going, what the heck's going on there? Full thrust belt shouldn't behave like this, and yet it was. When I looked at the nature of the strain in the Silurian quartzites across the region, I saw conjugate deformation lamellae in the quartzite ridges, the same type of conjugate disruptions in structures that you're seeing in shock quartz right by the Chesapeake impact. So on to chapter 5. That first part pretty much covered the first chapters, 4 chapters of the book. In the 5th chapter of the book, I go into this detailed analysis of the different structural astrogleams that you can see on Mars using the various remote sensing coverages that have been gained by NASA through time. The 75 to 82 Mars Viking 1 and 2 missions gives you the planetary surface in a natural color. And then we have the 96 to 99 Mars Global Survey data, which includes magnetics, gravity, topography, digital elevation models. We have it all now, ladies and gentlemen. And for the first time in history, we can assess these impact features with respect to these different remote sensing features, not only on Mars, but also on Earth, which is really cool. And one thing you see on Mars, which is really great, are these huge impact basins and antipodal flares of large igneous provinces directly across the way that I'll show you some of these. But I go through a number of these. I'm not going to waste a lot of time, but you can see the expression of these features reach 2,900 kilometer radius around them on Mars as well. There's the Hellas Basin, 1,600 kilometer expression, a big punched hole in the surface. There's the Sirius Sinai Planum that I talked about previously, and the oblique impact complex. And when I do the statistics and the histograms associated with all the different fractures and faults that I map in with respect to these different astrogleams, it comes up with most of them coming from the southeast and fanning out again. For some reason, the southeast horizon is where a lot of these things come from the basis of my interpretations. And I really don't know why, but that's those are the statistics. When you see the really large impact basins on Mars, like the Hellas Basin, here's an antipodal large igneous province directly 180 degrees away from it on the planetary surface. Here's Olympus Mons, Tharsis Montes, and Valley Marineris, and the impact complex that I pointed out for Sirius and Platinum. Here's Hallis Basin and a large igneous province associated with that. In Google Earth and Google Mars, you can build these axes, bring them in, and test the hypothesis of whether the Hallis Basin has an antipodal large igneous province, which you can see right here. I also built a 0 kilometer sea on Mars because I was thinking, well, if these things are going to be impacting oceans versus dry areas, where were the oceans on Mars? And I was able to generate one based using on the Mars Global Surveyor digital elevation model. So one thing I want to point out, and not many people know this, on Mars, there are almost hemispheric transecting faults that offset the magnetic striping of Mars. So these large impacts sometimes almost are completely penetrate the outer asthenosphere and basically offset, primordial, I think, striping that you see in the original segregation of the planetary material when it was cooling. You probably had bands like you have banded ironstone formations today. So these represent iron-rich bands, perhaps silica-rich bands, but these bands get offset as a result of these large impacts like Utopia. These large faults are parallel to the trajectory that Utopia of the asteroid that formed Utopia as it was coming in from an interpretation standpoint. Now, there's a paucity of information out there regarding the nature of impacts into spherical objects. Most impact experiments are done on soft plates of aluminum or sand or something at these hypervelocity gunning ranges like in Ames, California for NASA. But I devised a set of benchtop experiments to fire air pellets into silica glass balls to see what the astrogleam signature would be. If you will. I didn't know if this was going to work. It ended up working really well, which was a really, really big surprise. But here are the results of that, and I'm not going to belabor it much. But basically, I clamped these 60 millimeter glass balls into these clamps and fired steel pellets into them at pretty much the maximum pressure that an air pistol could generate. And the way that I varied the impact angle was I just basically raised up the gun each time using 1/4 inch thick sticks, so that the impact angle would be, systematically go from normal to a low angle impact to a moderate angle impact. And when I did that, I charted up the results and I took a look at what the different statistics were, the up range versus the down range effects. You can see the down range effects from an oblique impact are more so than they are on the up range side. But one of the big thrills associated with this experiment was the fact that at the maximum velocity that I could generate with the gun, at an 85-degree impact angle, I generated a foreland downrange tongue where almost the entire sector was popped out of the ball. But I think this is the geometry that we see in these large impacts relative to the excavated areas of like the Gulf of Mexico versus the disruptions that we see in the foreland. So that was a really, really nice experiment, and I would love to actually do more of this going forward. But I varied the impact angle from high angle to low angle, and you can see the variation in the patterns vary. At low angle impacts, you see these lateral sectors emphasized where the impact fractures propagate out laterally, preferentially, as opposed to the near normal impacts or the moderate angle impacts. When you plot up the results, you can back out a geometric progression. It's actually a power law relationship in terms of the size of the astrogleam versus the angle of impact, with all other conditions being similar. The other cool thing about this set of experiments was that this big impact that created that foreland tongue also created antipodal cracks on the other side of the ball. So it just basically cracked the crack from the transmission of the energy through the ball. I'm not going to spend much time on this, but I really hope that you buy the book and immerse yourself into this, because I've spent a great deal of time now integrating geophysical seismic velocity layering into these structural models to explain the nature of these, our layering. And what I was trying to get at when I was doing these models is try to understand the nature of the deep plumes relative to some of these impacts. The plumes coming off of the liquid outer core, which is shown in red in the two images on the top and onto the left. So this is a whole Earth mantle plume model that I built using this Mulick and Ekstrom 2014 whole Earth layered model, and brought it into a CAD system and built it in order to investigate the nature of our plumes and with respect to impacts. And here's what I found. Here's one of the layers from their model showing geographic space. This is the entire Earth with the slow transmitting areas shown in blue. Oh, excuse me, the slow transmitting areas shown in red, which correspond to the mantle plumes, and the cold areas are basically fast transmitting areas. And when you look at the different distributions of the plumes under Africa or the West Pacific, you also see that you have a lot of cold material under the North American continent, under Eurasia, and coming all the way down through the Asian, Australian region. What I was able to do by superimposing the world set of plate drift vectors on here, it occurred to me that you could fit basically the way that the plates are moving around the entire Earth based on two sets of great circles. One that rotates around the Hudson Bay and Antarctic set of dipoles, and one that rotates around the Nazca and Sri Lanka set of dipoles. And you can see the proof is right in front of your eyes. There are two sets of dipoles that describe all of the plate motions on Earth. And that's really, really quite amazing. It's even more amazing when you put it into perspective with the deep plumes. Here's the set of spreading ridges, subduction zones in purple, triple junctions shown in blue, and these plate vector motions shown in red. The amazing thing that emanated out of this model was that there are only two places on Earth where there's a direct shot from the liquid outer core through pipes that go right up to the base of the lithosphere, through the asthenosphere, through the mantle. One is in East Africa, and the other one is in the French Polynesian area. These things are plumes that are billowing up through the Earth, and they're the only two places where there's a straight shot under these two places. The East African core pipe leads to guess where? The East African Rift, the cradle of man, Ethiopia, where mammals evolved. Think about that for a second. The deep plume under Africa straddles the Vredefort impact crater, the Vredefort astroblume. So the deepest mantle plume that we have coming off of our core, helping driving plate motions, is centered on the Vredefort impact, which is the largest astroblume on Earth's surface, 2.2 billion years old. The magnetic equator shoots right through it in terms of the total field intensity. So these things not only set up and influence plate tectonic motions through time, they influence where the plumes are located, and they influence the way the plates are moving today. Now, if you haven't heard everything, that probably sounds very preposterous at this point. Let me just throw some other stuff out to you. There are a number of blemishes out in the West Pacific Ocean that look to me to be astroblooms. 125 million year, 93 million year, and you can constrain the ages of these things by the isochrons that they seem to disrupt. We have very, very detailed isochrons all over the world's oceans. Here's the 100 million isochron right here. And basically all of these features in the old Western Pacific predate this 100 million year isochron, or older Cretaceous events. This is chapter 8 in the book. This one is spectacular because it folds the isochrons on the ocean floor. This is the first case that I'm aware of where a strewn field, 125 million years, actually warps, folds the ocean floor. I'm not toying with you. These are the actual isochron traces, and they're folded into synclines and anticlines. These things structurally disrupt and fold vast regions of Earth's surface when they hit. And look at here, right here. This is the oldest oceanic crust in the world, right here. And guess what? It's remagnetized right out in front of where the focused energy was from this event. This is a demagnetized and remagnetized region, and the isochrons only come in around the wake, around the downrange part. This is the way it looks on a gray shade seafloor physiography, the remagnetized region, and oh, by the way, the subduction zones are, this is heading right towards where the subduction zones are. Uprange, downrange. Now I'm going to talk about chapter 9, 3 major impacts in the South American region. One is the Nazca, one is the Zingo Basin in the heart of Brazil, and one is in South Georgia right here. 24, 124, and 16. Now 124 is very close to the age of the one in the West Pacific, and I don't know how to account for that, but I can show you the reasoning behind the age that I've assigned to these. And by the way, this is the Earth Continental Geology by Era theme. So these are the youngest Cenozoic, the oldest Proterozoic in gray, Mesozoic in green, Paleozoic in pink. And you can see cross basin transcontinental lineaments, diamond mines, kimberlite pipes in the wake of this thing. Over here, 24 million years old, crustal disruption of the Nazca region that is very, very apparent, as is this Scotia plate. Here's the Nazca. Guess what is at 2,900 kilometers away from the Nazca? The East Pacific lies. Perfectly circumscribed by the major reflector coming off the outer core boundary. I think it raised this Nazca Ridge, which is responsible for actually where the Nazca lines are located right here in Peru. But this thing structurally disrupted the entire region. I think fragmented some plates, and look at the curvature of the South America continent with respect to it now. Here's the Xingu Basin. Again, a buried basin, much like we see in Chicxulub and Chesapeake. The crater's probably under these recent sediments. But here is the structural anticlines and synclines. Here are the kimberlite pipes. The first oldest age is 122 million years, directly uprange, where you would expect it to be. And then this is all actually evolved into the Trinidad volcanic field since then. But here are the gold mines and the diamond mines in the wake of this. I think these things disrupt the down to the asthenosphere and release kimberlites. But this is what was really ridiculous. I found an article that maps out the elastic thickness of the crust under South America. And guess what? The elastic thickness of the crust is compounded just where you would expect it to be downrange of the impact crater. I go into the Altanin astrobleem, which is really quite an interesting feature, because we know that this really young astrobleem occurs just north of Antarctic because of the strewn fields that have been picked up by the shipborne drilling out here. But using the gravity and magnetics, I think I've located where this possibly could be. And it, like the West Pacific astrobleem, where the ocean floor is folded, I think this also folds the ocean floor. And this occurred right at the dawn of man, 2.5 million years ago, down just north of the Antarctic. But I saved the best for last, because when I found these or proposed these, the extent of my research was down to the 2,900 kilometer level. I was seeing 2,900 kilometer arches and rings around these different features with repetition. in most of these things I was looking at. But when I looked at the Kara Sea, which I think is responsible for the Permo-Triassic extinction, and the Congo Basin, which is the other big basin, the Triassic-Jurassic extinction event, these are 5,000 kilometer range around these two big events. And look how they perfectly circumscribe the Pan-Euro-Asian mountain chains. Together, these two astrobeams have focused the location of subsequent origins mountain building regions on Earth as a result of the energy associated with these events. Let me go into them very quickly. Here's the Congo Basin gravity. I think it came in from the southeast. Camp, the Central Atlantic Magmatic Province that we have in our backyard, is over here and downrange of this thing. Here's the reconstruction of the South American Congo Basin impact relative to what Wagner noticed, which was the alignment of mineral belts and geologic belts when you reconstruct Pangea. This is what it would look like. The red are diamond occurrences. I think these things explain why diamonds are located where they are. There's the Central Atlantic Magmatic Province, and if you're saying, well, wait a minute, that would make more sense if the Congo Basin was coming in this way because we've seen melts in the wake. Well, I don't know why, but it appears to me that it came in from the south on this one, and the Central Atlantic Magmatic Province developed up in here, and this is up in the Newark Basin area up in here. So coincident, large impact, big extinction event, large igneous province development. But the big one corresponding to the largest mass extinction in Earth history, I think, is associated with the Siberian traps, as I mapped out here in Google Earth. Suspected impact location here under the Kara Sea. And I think this is responsible for raising Greenland up out of the water. Because if you look at the current spreading centers in the basin associated with it, the foreland region, and old spreading centers in the Beaufort Sea that were abandoned once this thing hit and positioned everything, you look at the magnetic expression of this, it looks almost exactly like the magnetic expression of the Chicxulub in the Gulf of Mexico. Right here. Here's Greenland. And when you do a reconstruction of this thing, oh, I don't have it on here, but it looks pretty convincing. To end the book, I go into a period of stasis. In between these catastrophic events, 99.99% of the time, we have uniform, gradual tectonic processes that we have come to characterize as those agents of plate tectonic theory that we all are aware of and familiar with. And in our particular region of the Northeast, I took the most recent GPS data, did the derivatives of the vertical and the horizontal drift over the region. This is the vertical derivative of the way the crust is sinking and rising right now through our region. And I'm trying to relate this to seismicity in the Philadelphia to New York areas. So these areas are rising in yellow. The areas in blue are sinking. The green areas are sinking slowly. So the only rising areas are basically south of the the Canadian Shield, are these little spotty areas out in front of the Chesapeake impact, to be honest with you. But if we take a look at the distribution of the earthquakes and the seismic zones associated with these crustal deflections that we see, we have the Ramapo seismic zone, which you've all heard about, the Lancaster-Redding seismic zone right here, the White Mountains up in here, Ashtabula, Southern Virginia. So this is the USGS catalog. And if I go into Sykes from Columbia, his catalog of the most recent and best documented occurrences of earthquakes from Philadelphia to New York, here's this Ramapo seismic zone right here. Here is the rising and sinking crust. And I think what we're seeing are seismic zones that are lining up along these troughs and arches that are forming as a result of a current compressive regime we have today during these periods of stasis. And if you look at the model in terms of where the earthquakes are happening relative to where the Cortland and Beamerville Ordovician intrusive complexes are. You see that most of the earthquakes are being focused around where these igneous plutons are, as if the plutons are pinning the crust to the mantle and resisting plate drift, which is really kind of cool. Also, check this out. If this is our GPS data saying that this is an area that's subsiding right now, and this is an area that's rising, the Collins Kill Arch and the Allentown Trough, we have a series of cross-strike folds that are occurring right through the New York recess that are parallel to the seismic swarms. And look how the Watchung Mountains sit exactly within that trough. Really quite remarkable. So, what do we take away from all this? Punctuated equilibrium is a more suitable guiding principle for terrestrial tectonics than uniformitarianism. That's sacrilegious, I understand, because uniformitarianism is the current guiding principle of geology. But very large hypervelocity comet and asteroid impacts on Earth and Mars impart far-field impact tectonic strains and have geodynamic consequences that are unaccounted for in our current theory. And I'm hoping that the paradigm will change, probably posthumously for me, but whatever, I'm just trying to get it out there. So large bolide impacts likely help form the mantle layering owing to repeated percussion and accretion. Think about that. Instead of the Earth having its layering form merely as a mineralogical and temperature pressure based phenomenon, what about these incessant cyclical percussion events where the outer layers of Earth get repeatedly fractured? What are going to be the consequences? We're going to have overlapping astroblumes and a strained, hardened exterior shell, predicated by the geometry of seismic wave responses. Now, in conclusion, mountain ranges and large basins can form suddenly in addition to slowly. I went into geology with the intention of understanding why mountains rise. Now that I think I understand why, it's not really a very popular idea. Planets are occasionally subject to cosmic storms, producing catastrophic geologic disruptions that are seen in both biological and tectonic records, and it may be the basis for ancient historical human accounts of seemingly improbable cataclysms like great floods, blood rain, and prolonged severe climate changes. I recommend getting and reading this book, Comet, Asteroid Impacts in Human Society, because in there, they use dendrochronology and ice core chemical analysis that show that within the past 4,200 years, we have had 4 extreme atmospheric disturbances, with the latter one roughly correlating with the onset of the Dark Ages. So, ladies and gentlemen, these events, even the smaller ones that we see like Tunguska, the volcanic winters, these events probably stem from cosmic events that disrupt our Earth on a continuous basis. But the bigger ones that we're talking about only on a 20 to 30 million year cycle, with the last one happening, probably 7 to 10 million years ago. So we seem to be safe from the bigger ones in the near future anyway. So that's it. Thank you for your time. And based on what I've been seeing, keep your watch on the southeast horizon. Thank you very much.
Okay. Wow.
Can you hear me?
Yep, I hear you.
Pretty awesome. Oh, I can't hear anybody. Hold on. Can I hear you now?
I'm here.
Okay, cool. My speaker shut off.
Okay. Oh wow, that was a mind-boggling program. Gets me thinking a whole different direction there. But we got some questions in the chat. You want to help with that, Melanie?
Sure thing. I'm looking at them now. Let's see. So someone asks, when you say a mountain range was formed in a short time range, what really is that time range?
That's a great question. Let me tell you a really quick story. When I first presented this work, it was in 2005 at the National GSA in Philadelphia. And I was working as a research scientist at the Geological Survey, and I was doing things that were way beyond what I should be doing for the Geologic Survey in New Jersey. But I couldn't help myself because I was finding this stuff doing a neotectonic analysis of the region. I presented at Geological Society of America, and I was afraid to actually present in front of anybody, so I did a poster. And the only person that really expressed an interest in what I was trying to say was this guy from the USGS who wore his brown khakis. And you know anybody from the USGS, that's like they're field people, right? They're the brown khaki laden field guys from the USGS. And he took a look at what I was doing, and the only comment I received from the entire poster session was from this guy. He says, "Go take a look at booth number 58." And so I shut down my rather disappointing, poster session that nobody just looking at me as strange. And I went over to booth 58, and there was a guy who's doing geochronology on the Laramide uplift. And he was showing that basically one pulse of the Laramide was within 5 million years of Chicxulub. And that was a great constraint for me, because I'm thinking, okay, well, these large scale uplifts that occur from these isostatic adjustments, from the absorption of ground energy, how long does it take for all that to adjust isostatically in the asthenosphere, et cetera? I have come to realize that a lot of the mountains can form like from land tsunamis. I'm talking instantaneously. Because if you think about what I showed you on Mars with the Sirius Planum impact complex, those wrinkle ridges and stuff didn't form anywhere but seconds to minutes after impact. So we're talking about mountains that are being raised instantaneously, not even Terry Engelder from Penn State admitted his confusion with the Alleghanian orogeny of Pennsylvania, because from what he could tell, the Alleghanians formed within a 1 million year time span. Accelerated tectonics. And I would agree with that. I would say that, yeah, a lot of the folding in the Juniata Combination and the Susquehanna region of Pennsylvania took place almost instantaneously, probably less than a million years, probably within days or hours of the event. Because that's how long it takes for a seismic energy to refract away from its source. So that's what I would propose. But, I'm going out on a real thin limb when I say stuff like that, because all we've ever thought about is just these plotting, uniform, centimeter by centimeter built mountain building episodes. And when you look at them, you go, how can that mountain sustain strains to form these big alpine folds if it wasn't like rumpling the carpet? I think our carpet gets rumpled. I think these things happen instantaneously. But that's just me. So does that answer that question, Curtis? And yes, Joe, remagnetized meaning heating past the Curie point. Yes. Yeah. These igneous provinces and these energy fluxes, I think, reset the magnetic clock. Could they cause magnetic field reversals? Absolutely. In fact, the last magnetic field reversal that we have, anybody know when it was?
70 million years ago.
800 million, between 788,000 years ago, 800,000 years ago. Guess what that also coincides with? The Austro-Laurasian tektite field. The largest tektite field known on Earth is at the same time of our last geomagnetic reversal. Now, the reason that I pointed the one chapter on the mantle dynamics out to you is because I followed up this work in my second book. I have a chapter on the mantle dynamics and how I think that our electromagnetic field reflects the relative proportion of magnetic material in our mantle. So if we have more magnetic mantle material in the south hemisphere, we're going to have a southern magnetic pole, negative pole. If by these impacts you generate these large igneous provinces in the north hemisphere, you're going to, and you have more melt material in the north hemisphere than the south, I think you're going to incite magnetic reversals. But that's not what the geophysicists say. They say it's all done by instability in the toroid, in the inner core, in the outer core. The churning away of these different convection cells in our outer core. I think a lot of it has to do with the mantle, because we have direct connections from the outer core all the way up to the surface. Why wouldn't they be magnetic? They're magnetic material, but it's just me. So Deccan lava flows due to impacts on the other side of Earth? No. I think the Deccan are actually in the immediate wake of the Kara C impact, which would be a corollary for what we see up on Mars with Olympus Mons and the Sirius Sinai Planum. I know people have said that Deccan are antipodal to Chicxulub and all that. And it's simply not true. They're not antipodal to Chicxulub. How much of the crustal rising in the northeast zones might be due to isostatic glacial rebound? All of it, pretty much. Yeah. And, you remove 2 kilometers of ice from the surface, it's going to rebound. Yes, it is awesome conjecture.
Wow.
The Great Lakes area that caused the Younger Dryas? Oh boy. Who had Andrew? That's an awesome question. I've been looking at that, and I've got something that I could share with you if you want to. If you want me to bring up Google Earth, but yeah, I think there is evidence for multiple impacts in the ice sheet up around Michigan Basin. Yep. So. And I think a lot of that evidence stems from the Carolina Bays. The Carolina Bays being, I think, ejecta deposits, ice ejecta or something that was thrown out as a result of an impact up in the ice sheet around the Younger Dryas. Absolutely. Yes, I'm glad you agree. That's awesome. Are there any more questions?
How do we find your books to
Just Google it on Amazon. They're all on Amazon. I got inspired. I have been the story of impacttectonics.org stems from my time when I was working at the state, doing research scientists on fractured bedrock aquifers, and that's how Jill and I met. He would have pollution sites, and we'd doing stuff together. I forgot where I was going with that. Hold on. There's another question here too. What was I saying? Help me out here, somebody.
Just about the books.
Okay, so they're on Amazon, and impacttectonics.org. If you Google that, you'll see links at the top of my pages for those books. And I'm not gonna, get rich by them. I'm only trying to get the record out there because I was only blogging about this stuff, and I got contacted by a lead exploration geophysicist in Alaska. His name is David Boothman, and he works for Hillcore Corporation. They were just in the news because they just got a lease from the U.S. government for an Alaska North Shore project. He just published a book called Impact Crater Tectonics as the lead geophysicist for this exploration firm, because over half of his play are on circular features, astrobleeds. And he said, this is ridiculous. I have to write something about this because nothing's been written on this. So he wrote a book about the same kind of stuff that I've been talking about, but from an exploration standpoint. And he sent me a copy, and it inspired me to write mine because I said, you know what, he can do this. He can self-publish something. I couldn't get this published. I've tried to get this stuff published in journal articles for the 5 years, and it won't even let him get it into review.
Huh.
They won't let me get it into review. They nix it before. They accuse me of drawing geological crop circles. And some of you may feel the same way. You know, this story is not for everyone, but honestly, it's the only thing that explains the conundrums that I've faced in my career as a result of putting two and two together and taking a look at the new plethora of geophysical and remotely sensed data, where, by the way, ladies and gentlemen, with the advent of GPS, now for 12, 15 years ago, it's the first time that we've been able to introspectively look back on ourselves for the first time in history. And the reason why we haven't found these things before is because we didn't have the tools. We see them up on Mars and Mercury and the moon, but we don't have the tools to look introspectively back on our own planet. But now we do. And when you look at it and you put two and two together, you realize that only half of the plate tectonic story is being told.
Huh.
The Earth and every planet was formed by bombardment and accretion. Where are those effects in plate tectonic theory?
Wow.
They're not there.
I think we need I think you need to do another talk at GSA sometime.
I did. I've done talks at GSA, but you know, quite honestly, they're very disappointing because you get 15 minutes.
Right.
How much can you say in 15 minutes? You know? So I appreciate the opportunity to do it here because you get to say what you want to say and
Wow.
you get some feedback. And Joe, thanks a lot for the invitation. I really appreciate it.
And we thank
Quite
you.
welcome, Greg.
Thank you, Joe, for getting the word back to us too, for doing that. So I just reading there, Andrew wrote about he has one of the Dirtman reports is about the Myrtle Beach impact craters in down in the Carolinas there.
Well, you wouldn't believe what's being done on the Carolina Bays. Somebody has gone so far out and done so much on these things that I think they've done actually too much and overinterpreted. But there are really quite remarkable features associated with the Carolina Bays that make you think that you know, there's probably a good reason that Clovis and Megafauna had disappeared about that time. You know, in terms of the extreme atmospheric disturbance associated with those things.
Okay, now that when you said about the Pennsylvania Appalachians, that kind of got my attention.
Yeah, I think a lot of that's Chesapeake, and again, you know, you can't discount stuff that's happening in the Mesozoic rocks. You know, I didn't even go into some of the really cool hydrogeologic aspects of this. The most open conductive fractures that we see in New Jersey are those associated with the Chesapeake event and current plate drift. So, you know, I was seeing east-west oriented fractures that are moderately inclined shear planes that you don't get through extension tectonics, and they are the most, you know, open water-bearing features in the water wells. And it makes sense because it was the latest punch that we received. Why wouldn't it be the most open? You know,
Right.
so it makes a lot of sense. I'm giving a talk, this same talk to my alumni at Ohio University in 3 weeks at a symposium there. And I'm really looking forward to that because I get to, you know, present it to the guy who influenced me to go into structural geology. And again, it's heretical, but it makes a lot of sense to me.
All right, my last question to you, Dr. Herman, is there a way I could see your master's thesis someplace?
Yeah, it's all online. Just go to impacttectonics.org and
Okay.
on my webpage, you'll see my publications page and it's all on there. But quite honestly, it's embarrassing. I was coloring with colored pencils and rubbing appliques on things, before digital cartography. It was the old fashioned way. So it's pretty crude, I have
Okay.
to admit, where things get like squished in the copy machine, they come out all skewed and stuff, but that's the way it was back then, doing that stuff.
Right.
Not like today. You have the world at your fingertips.
Okay. We thank you for doing that.
It was my pleasure. Let
Program.
me know when I can check it out on the video link.
It will
I'd
be
appreciate that.
it'll be up later tonight in probably about an hour and a half.
And Melanie, thank you for your help, and Jerry, appreciate it.
Our pleasure. That was I may not be able to sleep tonight. Thinking about the data you just gave us.
Well, I have other ones if you want. If you were looking to fill some time, I'd love to tell you about the Giza pyramids and Nazca lines too.
We'll keep that in mind.
Take care.
Okay, all right. We can't leave without another joke. I was invited to a meteor shower watch party one time. I couldn't make it. They were crushed. And so, yep, like Dr. Herman just said, the videos, all the Zoom room videos are on www.jonesgeo.com, Zoom Rock Room. This was the 102nd program that we did for Zoom Rock Room. So anyway, check out jonesgeo.com to look at the past programs if you like to. And we have some more exciting programs that are being scheduled this summer that might be of interest to everybody, I hope. So I'm going to pass it back to my co-host Mel, and she can sign off. Thank you for being here tonight, folks.
Yeah, sure thing. Like I said, as always, thank you, Jerry. Thank you, Dr. Herman, everyone for showing up this evening. Hopefully you can take away something from that amazing presentation. It was very interesting. And I hope everyone has a great night, and we'll see everybody back here in about 2 weeks.
See you, everybody.
Bye-bye.